Hi everyone, we are on day 22 of the challenge, which is the start of week 4. And today we have to do the basics. And it is about, it is GAN or GAN, I don't know, I'll say GAN. Understand GAN architecture and set up the framework. So let's go and ask from ChatGPT. I'll say, hey, it is the, I'll just move it here and let's say hey it is day 22 and here is the question. Okay, today is something new. The week is about something new that we have never done before. Let's see how it looks like. um okay, so today we dive into the basics of generative adverse serial adversarial. Let me ask how to pronounce it. Pronunciation. Adversarial. Okay, so it is generative adversarial networks are a really exciting and creative area of machine learning, often used to generate realistic images, art, and even synthetic data. Let's cover the okay. Nice. Let's cover the architecture and set up the basic framework using MNIST or Fashion MNIST. So, adversarial networks consist of two neural networks. First is generator, and second is discriminator. Generator generates new data instances that resemble the training data. A discriminator evaluates the authenticity of the generated instances and distinguishes between real and fake. Okay, so it generates the data that resemble the training data. Now it discriminates. And how does it do? It evaluates the authenticity of the generated instances. Okay, and which helps in distinguishes whether it is fake or real. So these two models are trained simultaneously, like in a game-like setting. Okay, interesting. The generator tries to fool the discriminator by creating realistic looking data. The discriminator tries to correctly classify. Okay, so they seem like working against each other. Generator tries to generate an image, which is the goal is to generate an image that generate that looks like real data, and discriminator has to correctly classify it into real and fake data. Cool. This week is looking really cool. Actually, I'm really excited. So the GAN workflow is, the GAN takes in random noise and outputs a synthetic data instances, that is example an image. The discriminator takes both the real data, so generator takes the random noise, and the discriminator takes both the real data and the generated data as inputs and tries to distinguish between them. Okay, so it takes both the real data and the generated data. Okay, the generator is updated to produce better fake data. Okay, the generator is updated to produce better fake data, aiming to fool the discriminator. Okay, nice, cool. This process is known as adversarial training. So the adversarial training is that generator gets updated and it tries to produce the better fake data. The discriminator uh, will try to correctly classify between the real and the fake data, and it keeps on happening. That is called as adversarial training. So it is pretty simple. It is pretty simple. Now let's go to the implementation, and that way we can also understand how it works. So We let's import the necessary libraries and load the fashion amnesty data, which is a collection of grayscale images of clothing items. Okay, fashion amnesty is a grayscale images of the clothing items. Okay, let's import the libraries. Before that, let's first create a day22.py file. Let's add it to the Git repository. Move the terminal window a little down. Mention the problem as this is the problem. So let's go back to the code and start writing. Import numpy as numpy. Import TensorFlow as TensorFlow. How many layers we want? We want dense layer, flattened layer, reshape layer, leaky rectified linear unit layer, and batch normalization. So let's import from TensorFlow dot keras layers, import dense, flatten, reshape, leaky, and the batch normalization. Then we have to import the model from TensorFlow keras C model, import sequential. Then from, okay, for plotting we will visualize by plotting graphs. So let's import matplot.pyplot as plt. Then one more thing, we have not imported the database that we are importing directly. I don't like doing this way. So I'll say from TensorFlow keras datasets import fashion MNIST. Is that correct? Correct. So now the next step is load the data. So data is fashion MNIST load data. Correct. Now let's visualize the data. If I do this data and run the file today, Python day 22, the data looks like this. The data looks like that, but I want to see it in a better way. It is not, I cannot visualize it right. So what do we have to do? We have to use pandas to convert it into a readable format, that is pandas data frame. Let me see, read the documentation. Can we get it already in the data frame format? Uh, so it has 60,000 images, the size of 28 by 28 grayscale images of 10 fashion categories, along with a test set of uh, 10,000 images. The data set can be used in drop in place replacement for MNIST. Okay, so we can get it in Xtrain, Xtext, Xvitus. Uh, okay, so we can get the data in this format. Xtrain, Ytrain, Xtest, Ytest. Xtrain will be 60,000 28 by 28. Ytrain will be 60,000. Uh, 1D array where the labels will be in the integer form of 0 to 9. Okay. Y test will be 10,000 images of 28 by 28, and Y test will be 10,000 images. Okay. Again will be a 1D array which will be the integer form of the labels. The classes represented by 0 to 9 digit integer value 0 to 9. So we can get it like x train, y train, x validation, y valid. Let's visualize. So pdx data frame will be pd into data frame x train. Let's run it, print data frame, see if we get any error. If we will further see how to fix that error. That's yes. So it is not working. Let's do what? Let's do what? Let's see the shape x train, though we read it just now, but x train dot shape. So we will do what? Flatten it. So x shape flat will be x train, sorry, x train flat. It should be x train flat dot reshape of uh, 28, sorry, minus 128 into 28. So let's again see the size, and let me see if I'm doing it right. And it should be this. Sorry. Correct. The data is correct now. So now I'll do what? I will. It is correct. 60,000 images of this big size. And then if I do this, will I see the data frame correctly? Oh, correct. So it has worked. So I'll do what? Use the function info to see the information about this, and also parallelly I'll use a function called head to see what to see first 5 rows of this data set, of this data frame. So the info says that it has 60,000 entries, and from 0 to 9. The index is from 0 to 59999. Then it has 784 columns that we just reshaped. That is it. And the values inside this looks like this: 188, 156, 157, 76, oh yeah, 135, 168. So if I say df dot minimum value is, if I want to print, the minimum value here is, the minimum value here is, okay, uh, I'll say python get minimum value of our data frame column. So it is going to be, oh, see, it was right, minimum value, and then we want to see data frame dot maximum value. I was right. Why? Stupid, I am searching even after getting the right result. See, here we see the minimum value of each column is 0 0 0 0. The maximum value of each column is 1255. So it ranges, the data here, the values, pixel values ranges from 0 to 255. Let me close it. 20 to 255. Okay. So what are we doing here? We are normalizing between -1 and 1 because it helps the 10h activation function in generating work. in the generator work better. Okay, so we are using 10H today. We have learned about it already in the, if you go here 10H, day number 4. Here we have already learned about 10H, which is hyperbolic tangent activation function. It is very similar to sigmoid, but sigmoid the other one. But instead of outputting the values between 0 to 1, it outputs the value between minus and 1. So we are using this activation function, which outputs the value between minus and 1, minus 1 and 1. That is why we are normalizing it between minus 1 and 1. So for example, let's say exchange value is 255 minus this is 255 minus, so it will be 255 minus this is 255 minus this is, let me see, 255 divided by 2 is this. So 127 point, so 127 by 127 is 0 only. Now this is the maximum value. Okay, this is the maximum value 120. So it is 255 minus 127 is 127 only, divided by 127 1. Let's say if I have any lesser value, this result will be lesser, and this will be lesser than 1 always. Okay, now if I have 0, 0 minus, so if I have 0, any value lesser than 127 will be will result this negative. For example, 0 minus 127 is minus 127, divided by 127 is what, 1. So it will range from minus 1 to 1. So let's do what, let's hide it, and we are doing what, normalize between minus 1 and 1. Why? As it has 10H activation function that we will be using. Okay, so we'll do what, x train will be x train, so let's put it in the braces, 127.5 divided by 127.5. Okay, now we will reshape it. What are we doing here? We are reshaping it we are reshaping it and adding a column channel dimension, also RGB color, which is necessary for carriers to understand that these are grayscale images. So that is why we are adding one more channel. So we'll do what, x train will become what, x train dot reshape. Here we will reshape, we'll keep the size of this as this, which is, what was the size, yes, x train dot shape, the size which is 60,000. And then here the size changes 28, 28, and then we will add one more as dimension, which is useful to for the carriers to show that this is a grayscale, they are grayscale images. The type is going to be float 32 FLO 84. Cool. Now let's clear the terminal, move it a little down, come back here, and let's build the generator. Really excited to see what it is going to build. Yes, let's build. So the generator takes random noise and generates a synthetic image of the same shape as the, okay, so it takes the random noise and generates a synthetic image of the same shape as of the input MNIST images, which is 28 by 28. Okay, so it generates noises of the same shape. That is the full context. So here we are doing build generator. What is it is doing? Build images of same shape of as of input MNIA fashion MNIS so data which is 28 by 28 build whatever it is and rate yes. So let's do what, let's put it here, and now we'll do that. So define the generator. So definition is build generator model, sequential model. Okay, let's see if it has any description. So it has layers. Dense layer to increase dimensionality from noise. Random vector. Okay. To build the dimensionality, to increase dimensionality from the noise. So we are increasing dimensionality. So the input dimensions are 100, and then we are going ahead with 256 neurons. What did it says? The dense layer says the generator uses dense layers to gradually upscale the noise vector, that is 100 dimensions, into an image sized output. Okay. Then we have leaky rectified linear unit. Leaky rectified linear unit helps to avoid dead neurons that can happen with traditional. Okay, it helps to remove dead neurons that can happen because of the basic rectified linear unit activation function. Uh, then we have batch normalization. It helps stabilize training, allows the network to learn faster. Okay, these are new terms though. These are two new terms. So what I'm going to do, I'm going to close it here, and I'm going to keep create a new file, not here. I'll paste it here, and I'm going to learn about it later, because what I've seen is when we are learning, uh, let's build the model first and then we'll come back and learn about it. Okay, or what we can do, I'll say what it has more. So it helps in training, allowing the network to learn fast. Okay, it helps in training and allows the network to learn fast. We are doing it and we are adding the dimensions, adding more neurons with the same configuration of leaky rectified linear unit and batch normalization. And then we'll add more neurons here, which is of 1024 size. And then the final output layer is reshaping to 28 into 28 by 28 by 1, which is the input image dimension. So these are going to be the neuron size. Activation function is going to be tan h, which is going to output in minus 1 to 1 range, and then we reshape it to this, and then we will return the model. Correct. Let's read a little bit about it. Perfect. So let's see. Can you please explain this with easy and short sentences? What it does, it explains overly. So I tend to get confused and I'm a little sick. I don't want to. Yeah, nicely. Okay, so this leaky rectified linear unit alpha equals to 0.2. What it is an activation function. Okay, that I have understood. That allows a small non-zero gradient for negative inputs. Okay, So if you remember, rectified linear units was blocking negative inputs at all. If we go and read it here, it passes the positive values as they are and stops the negative value by turning them zero. But this leaky rectified unit, what it does, it allows a small non-zero gradient for the negative values. Okay. The parameter is alpha 0.2. Controls how much negative values, that is leak, is allowed. And this prevents dead neurons, which can occur when regular rectified linear unit sets all negative values to zero, stopping learning. Okay. So what happens? Dead neurons are like deads them, because if they have negative value, it is going to just turn it. Uh, is not going to pass it. So with leaky rectified linear unit, it passes a small amount of negative values, non-zero gradient for negative inputs, and we pass it like 0.2%, 20% of the uh, values needs to go. Like for example, the parameter alpha 0.2 controls how much the negative value leak is allowed. That is, it is 0.2 multiplied by x when x is less than minus 0. So if it is x is less than 0, which is 1, 1 divided by 0.2 is 0.2 into 1 is 0.2 itself. 0.2 into 2 is 0.4, 0.2 into 3. So yeah, that is why. So this is how it controls how the negative values. Then batch normalization requires the output of the layer to have a mean of 0. So it requires the output of the layer to have a mean 0 and a standard deviation 1. So it looks like this is a normalization. It looks like a standard scaling that we do apply on the models. So it what it does, it makes sure it normalizes the output of the layer. It normalizes the output of the layer by doing what? By having the mean equals to 0 and the standard deviation to 1. It helps to stabilize and speed up the. Okay, we have learned about how normalization affects the model. When the range is small, the model the the model is going to learn faster. Okay, and it is obviously going to be more stable. That is why here also stabilization is going to be helpful. This batch normalization. What is this momentum equals to 0.8? Momentum equals to 0.8 means that 80% of the old moving statistics are retained, while 20% come from current batch. Running mean and variance are updated during. Okay, so 80% means that all moving statistics are retained, 20 will come from the current batch. Okay, so batch normalization, so it is like it is doing it in the batches. So it says 80% is from the old statistics, 20 is going to be the from the new batch. I'll not go in the deep of this because I feel this is like I understand what it is doing. It is defining like how much of the data is going to come from the new batch and how much of the how much we need to retain from the current batch. And today is we need to focus on the GAN. GAN, I'll use GAN. Today we need to focus on the GA and GAN model, so we'll focus on that. So yes, in a way it is going to help and improve the learning. So I'll go back. We have understood what it is doing, so we'll go back and then define the layers. So come back here, so we'll do model dot add dense layer. We'll start with 256. Activation function is going to be no, so input dimension is going to be 100. Then model dot add, not mpl, model dot add a dense not dense layer, rectified leaky rectified linear unit of alpha equal to 0.2. Then we'll add model dot add a batch normalization layer of momentum of 0.8, 80% from current, 20% from the new batch. Then we'll add few more layers. Here it will go 1024. uh, it is going to be double 250, so 526 is multiplied by 2 is 512, correct? Everything is going to remain same. Then I'll also remove the input dimensions, we don't need that for the next layers. Then we'll have the another layer which is 1024 neurons, and we'll have final layer which is model dot add dot dense of 28 by 28 by 1. Activation function is going to be 10h, and we have just learned about it. Then we are going to reshape a reshape layer, and we are going to reshape into okay, let's reshape into 28 by 28 by 1. That we need to produce the final image, and we will simply return the model, and then we will build the model. The generator is build generator, and we print the generator summary. Okay, let's go back to the build the discriminator. We have understood what is the role of discriminator in the GAN model, uh, uh, generative what was the full form? Adversarial training model, adversarial network model. So it is the task of this is to correctly classify the fake and the real data set. So let's do what? Read a little before we implement. So it has a model, a sequential model. It has a layer called flatten, because now we are flattening the 28 by 28 into one image input, because the dense layer, the output layer will not understand it. It understands uh, flattened vectors. Then we have a dense layer of 512 images. Two dense layers we have with leaky rectified linear unit to analyze the input. Okay, so this is to analyze the input. So we are doing it in the same way as we did it here. And then we are going down from the higher dimension to the lower dimension. And then we produce the classifier. Then we classify with the final output layer, which will have one neuron, which will say whether it is a fake or real data set. We do that. So fake one will be 0, real one will be 1, and it is we'll go ahead with sigmoid data activation function. If we go and come back to the challenge that we have solved on day 5, we saw that if we want to generate the output in the range of 0 to 1, then we go ahead with sigmoid. That is, if it is true or not, because 0 or 1 represents extreme, then we go ahead with sigmoid. So let's do that, and then at the end we are going to compile the model and print the summary. So let's come back to the step number 3 and build the discriminator. Definition, build uh, discriminator. So I'll say model is sequential model, and then we have layers. Model dot add a flatten layer, flatten it to 28, 28, 1 input shape. Sorry, not data. Input shape is that. And then we have more layers to process the flatten image. So we'll add layers to process flatten image. So we'll do what? Model dot add dense layer of what? 5 and 2 size, and then add the rectifier leaky rectifier linear unit with alpha 0.2, correct? And then model dot add dense of 256. Model dot add, let's put key, take it, I mean keep it in the center. Leaky rectified in unit alpha 0.2, done. Then we add the final output layer to classify final output layer to classify real or fake. So we'll do what? Model dot, so real is 1 and fake is 0. So model dot add, what are we going to add? A dense layer of 1 neuron only. The activation function is going to be sigmoid, and we will return the model, and then we simply build the discriminator using the build discriminator function. Now we compile the model. We'll do model, what are we going to compile? We are going to compile discriminator dot compile. We'll pass the optimizer as the atom. The loss is going to be binary cross entropy because it is a binary. Let's go and read it. Yeah, binary cross, because used to classify images as real and fake, so it is binary classification type problem. So a thing it is doing, so it is, that is why binary cross entropy. Then we'll have metric. I guess I have a matrix. It is going to be, what are we going to see? Accuracy or loss? Yes, accuracy only. That is it. Now we want to see the summary. So discriminator dot summary. We are done with the step number 3. Yay. And we are almost done with the problem. Now what are we doing? Now we are going to build the generative adversarial network model. So if we are going to put the generator and discriminator together to create the model. So what we are going to do, we are during the training, we don't want to update the discriminator while training the generator. So we do not want to update the discriminator while we are training the generator. So that is why we are mentioning that don't turn the trainable as off. Then we are going to build and compile the GAN model. So what are we doing? We are building a model where we are passing the generator and discriminator. First we pass the generator and then we pass the discriminator and then we return the model. Again, we are not training. So we combine generator and discriminator sequentially. First generator and then discriminator. Where generator tries to fool the discriminator. Where generator tries to fool the discriminator. And one more time, we are making sure that it does not get trained while we are doing that. That is why we are marking it as untrainable, and then we compile this model. So build the GAN model. Build GAN, not capital, yes. So what are we going to do? We mark it as discriminator dot trainable false. And then what are we going to do? Build definition, build GAN, and here we mention model, a sequential model. The sequences first is, we'll add, it will take two models, generator and discriminator. Here we add the generator, and then we add the discriminator, and then we return the model. Here we build the GAN. So we'll say GAN, it is going to be build GAN. Here we pass the generator, discriminator, and this is it. Now we compile it. Compile it. Optimizer is going to be Atom, and here it is again. It is going to be binary classification because we have to classify whether it is a fake or real image. So it is going to be binary classification. Classification. That is it. Now we'll do what? Train the GAN model. We now train the GAN. We have now built the GAN model. Now we are going to train the model by iteratively training the discriminator and then generator. Here is the simple training loop. So this is something nice. You must be hearing my voice with very high pitch. It is because that I have very bad cold. That is why. So what are we going to do in this step? We are iterating, preparing a loop such that we are training the discriminator, and then we will train the generator to generate the images. So the training is going to be how many epochs we want. We want 10,000 epochs, batch size 64, and then we have save interval as 1,000. Let's read the description. It says training the discriminator on a mix of real images from the dataset and fake images generated by the generator. So we are getting the real images from the dataset and the fake images by the generator. This is how we are training the discriminator. Train the generator via GAN model to fool the discriminator. So we are training the generator. Noise is randomly generated noise is fed into the generator to create fake images. Okay. And save terminal, we print the progress and save generated image every 1,000 epochs. So let's read a little. So we are generating some fake images. So for the batch size of 64, we have some zeros, ones as 1, and zeros of size 64 into 1, 64 into 1. These are the real images, these are the fake images. Okay. For each epochs in the range epochs, for 1,000 epochs, for epochs in every epoch up to 10,000, train the discriminator. We get the random int from uh, the range is 0 to 60,000 that we saw. This is the 60,000 images. Uh, from 0 to 60,000, we have to generate. So it's just a second, right? Again forgot. What is the. So let's start up coding and then we'll understand. What are we doing? We are training the GAN. So let's do what? Let's define import the OS. This import OS. So we are doing what? Epochs. So we'll say training parameters parameters. So here it is epochs 10,000, and then we have batch size as 64, and then we have save interval, save after every 1,000 epochs, and then we label for real images, label for real and fake images. So what are we doing? Real is numpy dot ones, and here we pass the batch size 1. Let's print it first. I'll just comment everything because I don't want to waste. Yeah, let's what, run this and see if it is going to take some time. uh, I will comment it. So it is a vector of size 1 1 1 1 1 1 1 1 1 okay, of 60,000. So if I'll say it is shape, here it is, sorry, let's run it. The shape is 64, yes. So it is a 64 rows and one column. So in 64 rows it has one only, that is, so for 64 images the label is set as 1. For 64 images, the batch size, the label is set as zeros. So zeros, so it is fake, sorry. Batch size 1, we are done with that. Now we are iterating. What are we, so let's iterate. Let's clear it, move it a little down, and then do what, uh, for epoch in epochs, not here, range in epochs, we'll do what, so epoch will be 0 1 2 3 4 5 6, and train the discriminator. So we are doing train the discriminator. So we'll do what, index is numpy dot random int we have to generate. So here we pass the slow and high size data type out. Okay, so we tell what is the lowest value, the highest value, and to be drawn from the distribution. High, it will one largest integer to be drawn from the distribution. Size is going to be okay, and desired d type. Okay, the given shape m and k, for example, which is in case, let's see. So if it is going to be 0 to 60,000, so x train dot shape 0 60,000, and then we'll have batch size 64. So let's print the index and break it. Let's run it again. So see, we have image, the range. So how many values we want to generate? 60 values, 64 values we have to generate, and each will have the indexes, like, so we are generating random indexes of images from 0 to 60,000, and then how many indexes we want to generate? 64 indexes. So then we get the real images. So real images we'll get from the X train. Let's do what, we are not using it anywhere, so I'll just pass like this. If you remember, here also we are passing like that, no? Correct. So let's go come back to this step. So we get the extreme real images, extreme the indexes. So these are not indexes, these are random indexes, right? Random indexes. So random indexes. So we'll have real images. Now what are we doing? We are uh, getting the noise. So let's do what? Noise is what are we doing? We are generating a normal numbers from 0 to 1, and the size is going to be 64 into the original dimension, which is 100. So it is going to be numpy random normal 0 to 1 and batch size and 100. Let's print the noise also. Let's clear the terminal and run it. This is how it is generating. 64 into 100, 64 into 100. Sorry. 64 into 100. This is how it is generating the noise from 0 to 1. Well, done. And then what are we doing? We are generating the images. Generated, generated, generated images are from the generator. Predict this noise. We are passing a noise, and then yeah. Then what are we doing? Then we are doing this loss real. We are training on batch. The real images and the real. What real do we have? Okay, the real tag. Train on batch. The real images and the tag. Train on batch. Generated images and fake. These are the fake images. So we are training on that. We are the real images. We are training on that, and these are the reliable for them. So discriminator loss real and fake. We now calculate the discriminator loss by doing 0.5 multiply by we are adding up those two. This is how we are getting the discriminator loss. So let's do that. The discriminator real loss of real images is going to be discriminator train on batch. So here we pass the training data real images and the real label, the target, and then we have discriminator loss of the uh, fake images. So discriminator train on batch the generated images, and then we pass the label for those as the fake that we have calculated, and then we get the loss of discriminator as 0.5 multiply by, which is what are we doing? We are just averaging it. 0.5 is what? It is 1 by 2. So we are adding it up, multiply by numpy. So we are doing the mean. We are just getting the average loss of fake and real loss. So we added the real, the loss fake. And then what are we doing next? We are doing train the generator. We are training the generator. How are we doing that? So we get the noise. So we get the noise that we just saw. We generated, again we'll generate it, and then we train the generator. So the model will be trained, the GAN model will be trained on noise, and we, what are we doing? We are passing them as the real images. So now here the generator will do what? Generator will generate the images as if they are looking real images. So we are passing the noise. Generator will use this noise to generate the real images. That is why we are passing the real label, the label real images label here. And then discriminator has to do what? Discriminator has to the discriminator has to classify them as the real or fake. So let's do that. So what are we doing? Noise. We get numpy, random, normal, 0 to 1, and then batch size 100 dimensions, and then get GAN loss, and then we get the GAN train on batch. Here we pass the noise and the real label, and we do what? Print progress. We are printing the progress. So for every, what are we doing? We print the progress, save and generate an image every 1,000 epoch. What is this? Every 1,000 epochs. So let's understand this. So if epoch mod save intervals is 0, when it is going to be 0? It is going to be 0 only when the epoch reaches 100,000. The epoch number will reach 1,000, mod by 1,000 is always 0, or when epoch is 0 by 0. Okay, 0 by 1,000 is 0 only. Yes. So what? So I'll say print. We want to print the epoch, loss accuracy by multiplying it 100, and then GAN loss. Um, and then save the generated image to visualize the training progress. So let's print it first. Print epoch, epoch. What are we doing? Uh, D loss is D loss, and then we have accuracy as 100 multiplied by D loss, 1th value. Uh, this will be whatever it will return, it is going to be represented in percentage. Once done, what are we doing? We are getting the G loss. So G loss will be G loss. Okay. And then we save the generated images to visualize the training progress. Okay. What are we doing? Save the images to visualize the training progress. So we have got generated images as we'll pass the generator the noise generated image, and then we'll get the recall images from -1. So recall rescaling images. The images were in -1 to 1. We want to rescale it to 0 to 1. So what we are doing this? We are doing this 0 point. We are dividing it by 2 and then adding it up. This is, if you remember how we did the rescaling, you'll understand it. So generated images, we got it. So we did get it already, no? uh, Images will turn into 0.5. Does it, I don't know, does it do what? I'll just follow what it says. I'm just going to do ask, because does it changes the thing that we pass it here? Maybe that is why it is doing that. So the generated images will be 0.5 multiplied by uh, generated images, and then add it up to 0.5, What are we doing it? Why are we doing it? We are rescale back from -1 to 0 and 1 rescale. Okay, so what are we doing? We have rescale, and then we are going to plot, show this images. So we are plotting a figure, plot figure of size 5 is to 5, and then we are going in four ranges from 101 to 3, and we are plotting the images. So we have a subplot of 2 by 2, 2 rows, 2 column, and in this we have I plus 1 0, as in 1 2 3 4, 1 2 3 4 columns, cells 1 2 3 4. So in the first cell show the first images, generated images, and then this is how it is shown. So let's do what for I in range 4. What are we doing? Plot a subplot of 2 rows, 2 columns, and for cell this, for ith 1 plus 1 cell, plot this image from generated images, mention the I, and then pick the values. So the ith, the grayscale, and it is a grayscale image, and just put the excess flow. Why? Because then it starts showing 0 1 2 3 on the x scale and y scale, so we don't want to see that. And then we simply show it. Once it is done with plotting the subplots, we'll simply show it, and then let's do what, let's run this. We are doing it for the first 1,000 epochs only, but it is throwing an error. uh, so it says I have an error at line number 118. 118 is this. So I've got this error on this. Am I have I done it, like have I used the same noise again? Let me see. Let's see what ChatGPT has to say. Hmm. The error message indicates that the loss function binary classification is not recognized by the carriers. Okay. So we'll say binary is not recognized. So we'll uh, make sure that generators are properly combined and uses the correct loss function. Binary cross entropy. Let's me go and okay. I had a typo here. I'm so sorry. Let's do what, recompile it. So it is has generated in images like this. I don't see anything inside this. Let me come out of it, and then let me run it again. So this has generated the image like this. I guess I'll see the image again, if not this. Okay, it is open only. It is training, training, and training. So we see the images again. Okay, I don't, I'm not able to recognize it. So let me save it, and then it will again take some like a good 1 minute to generate the images. Let me see. So the loss after first epoch was 0.002 d loss, and this was the GAN loss. Um, uh, D loss is 0.002, and G GAN loss is coming as 16.22 after 100. So we'll again see it. This is how it is looking. I'll go and take it and ask ChatGPT. This is how it is looking. Just tell me. Okay. Uh, then 9.2, 0.004. Uh, how good the model is performing. These are the first two iterations. Uh, and let me put mint. Let me send it, and then ask from ChatGPT what ChatGPT has to say here. Not this. Why am I opening it again and again? Uh, so what are we doing? What are we doing? And the images produced by the generator are so far seem to be blurry and incoherent. The shapes are mostly random noise and lack by recognizable patterns. They don't resemble clothing items for sure. See, they don't resemble the clothing items for sure. Let me take screenshot. Uh, uh, they don't resemble clothing item from the MNICM dataset, which means the generator has not yet learned to produce it. Okay, so it has not produced realistic images. That's what I can see from here, from the images also, and from what the ChatGPT is explaining. Typically, the fashion MNIC, you'd start seeing basic outline of the clothing item like shirt, shoes, but the images that we see are pure noise. So and the loss analysis is, so the discriminator loss is quite low, indicating that discriminator can easily distinguish between real and fake. So the discriminator is working fine here. See, uh, this is the so this is performing really good. The discriminator is too good at telling real images apart from fake images. This can sometimes hinder the generator learning, as the generator cannot learn effectively if the discriminator is consistently confident in prediction. Okay, this can be one reason. Then the second is GAN loss is quite high. Yes, we see, as I see, if I go and see what was the GAN loss it had. So if I go and see what was the last GAN loss was 6.9, so it has dropped. Continuously dropping, and the D loss is continuously increasing also. So here, uh, and from here we see that here the epochs are continuously, it is continuously increasing here, whereas this is continuously decreasing. So it is facing the difficulties while generating, classifying between the real and the flake ones. But here it is getting better. The GAN model is getting better at generating the images. So it is getting better at fooling the, so the GAN loss is getting better, which means the generator is getting better at fooling the discriminator. If the discriminator loss is high or lower, which means the discriminator is performing really good work. So this is the, I guess, seventh. So if I go here, 17, so yeah, I probably will see two or three more images. So yeah, so this is how the GAN model looks like. We see blurry fuzzy images, but overall it is a good learning. We have learned something new today. I'll do what, I'll stop it and do what, add the code, because it is a great day. I have learned something new today, that what is this generator and discriminator and how they play a role, a game. Like, I have to prove you wrong. I have to generate images, they look like real but they are not real, and the discriminator has to classify them as real or fake. So the discriminator will try to perform good, the generator will try to perform good. So this is like a fun game. So yes, the learning is great from today's problem. Now if we'll come back, let me commit it first. So let me commit, uh, add, add uh, D22, build and explore GAN model, and day 22. Okay, so this is it. Let's push it to main branch, and let's go back here, and see if I can see the code here for the 322. So yes, we can see the code here. Really good. I'm really happy with how I have performed, or I have managed to make the video or solve this problem despite having the fever. So yes, what I'm going to do, I just want to, before closing, wrapping up this video, let's look at what we are going to do for the rest of the week. So tomorrow we are going to continue on what we have done today. We are going to train and evaluate the model. I guess we have done it today already, but yeah, I'll see what needs to be done today. So we just wanted to set up the framework. So we have already done that, but let's do what, tomorrow we are going to explore how to improve the model. Sounds good, right? So we'll work on how improving the performance of the model. And then yes, the whole full week is like understanding the transformers and the advanced topics. And then we'll whistle with closing the, doing the 30th problem. So I'm really excited, and I have really great plans on what to do after I finish this. So thank you very much. I'm not going to go and make the extensive hour-long videos like what I'm doing. I'm planning something different. I'll speak about it later on, maybe on the day 30th. But thank you.